Hello friends, so today we are discussing the continuation of our last session, that means capacitors. So the first we will discuss energy stored in a capacitor. We have to derive an equation for energy stored in a capacitor. So we are having a capacitor of capacitance C is connected to a cell of voltage V. Okay. Initially, the capacitor has zero charge. As we know, when it is connected to a cell, the charge will flow and stored in the capacitor. And the final charge will be capital letter Q. Okay, so initially the charge is zero. Finally the charge will be capital letter Q. We are taking like that. So we are telling dq is the small charge. To store this charge in the capacitor, the cell should work dW, small work done, as we discussed already. So dW is equal to potential into charge. We studied already V is equal to W by Q. So W is equal to V into Q. So here instead of W dW, instead of Q dQ. So dW is equal to V dQ. We got an equation. We already learned the basic equation of capacitance. V is equal to Q by C. So we are substituting that. dW is equal to Q by C into dQ. Then for calculating the total work done, we are integrating dW. So W is equal to integral 0 to Q dW, because I told you initially the charge was 0 and finally charge become Q. So we are substituting instead of dW Q by C dQ. The constant term 1 by C took outside, because as we know Q is a variable, because as the time increases Q is also increasing because capacitor is charging. Then we are using our usual equation of integration. We studied integral x raised to n dx is equal to x raised to n plus 1 divided by n plus 1. Here instead of x q, instead of dx dq. N is 1 here. So we will get q square by 2 as the result of integration. Q raised to 1 plus 1 divided by 1 plus 1. Then we wrote the limit bottom and top of the square bracket. We already discussed that. Next we are giving the limit. I already mentioned upper limit minus lower limit. So upper limit capital letter Q we are giving instead of small letter q. The lower limit 0 we are giving instead of small letter q. So you will get a W is equal to 1 by C into Q square by 2 minus 0 square by 2. So the second term vanished. You will get W is equal to Q square by 2C, where Q is the charge stored, C is the capacitance of the capacitor. This is the work done stored as the energy, potential energy in the capacitor. We are having two more equation, alternate equation. Potential energy we are giving capital letter U, Q square by 2C we already derived. We are substituting Q is equal to CV. So you will get CV whole square by 2C, because Q square is there. So once C get cancelled, you will get half CV square. Another equation for potential energy stored in the capacitor. Again, we are substituting half CV square. Then we wrote V square as V into V. So half CV into V. What is CV? You can give Q. So you got another equation, half QV. So we are having three equations for the energy stored in the capacitor. First one Q square by 2C. Second one half CV square. Third one half QV. That we already discussed. So according to the question, if you want to find anything, you can use according to the given thing by choosing these equations. Okay, any one of the equation you can choose according to the given parameters in the question. Okay, so this is our first derivation. Then we are discussing the it's not that much important, but it's a subsection of this first session, energy density of the capacitor, where as we know energy density means energy per volume, because density the term you already learned. So energy we already derived half CV square. Then volume, capacitor area is capital letter A and the distance is, or the distance between the plate or length is D. So area into length is volume. Okay, so instead of volume we gave A into D. So what we got, we already derived parallel plate capacitor having capacitance equation epsilon 0 A by D. So we are substituting there. So half into epsilon 0 A by D V square by AD. So A get cancelled. We will get epsilon 0 V square by 2D square. Otherwise, you can write half epsilon 0 E square. How that E square will come? E square came because as we already learned, potential and electric field is only difference with one distance. Electric field 1 by 4 pi epsilon 0 cube by distance square. Potential 1 by 4 pi epsilon 0 cube by distance. So if you are dividing potential with a distance, you will get electric field. Okay, so the equation is half epsilon 0 E square. Then it's also an optional topic, but you should learn. Okay, Van de Graaff generator. We heard generator. Okay, generator, AC generator and DC generator you learned. AC generators and DC generators are producing energy, mechanical energy converting into electrical energy. This is not that type of generator. This generator able to develop high potential difference from the given small potential difference. That means you are giving initially a small potential difference. This instrument is multiplying the potential difference what you gave. You will get 10 raised to 7 volt maximum if you gave 1000 volt or 100 volt. I hope you clear. So what we gave, it's multiplying. And this is the picture schematic representation of that Van de Graaff generator. It consisting of a from the top I am discussing, it consisting of a spherical what is called a shell. Remember it's shell, but that means it's hollow. Inside two pulleys are there, top and bottom. The pulleys are connected by a insulating belt. That means that belt is insulator. And these pulleys are driven by a motor. That's not shown because I don't want, that's why. So the arrow mark you can see. So the pulley and the belt system moving up and down, very clearly. Then this whole arrangement is kept in an insulating stand. Okay, it is consisting of metallic brush. Okay, brush means as we know, our ordinary brush with some bristles. Okay, it always makes a feather contact with our teeth while brushing. It is not damaging our teeth. Like that, in a rotating system, we are using brushes. As you studied slip rings, split rings in generator, that's same. Brush ring system we are using as accumulator or something else. So let me tell that commutator system will work here. No need to learn that much for that. You should study, there are two brushes. Bottom part you can see C2. There we are connecting the positive terminal of a battery. So from the positive terminal, the charges are flowing and reaching to the brush bristles. This bristles, metallic bristles, okay. This bristles always touching the insulating belt. Okay. Remember the belt is insulator and moving up. That's left side I am telling. So it will carry the charge as a conveyor belt. You understood, I think. Because it's an insulator, so charge will not go anywhere. In the top, there is another metallic brush C1, you can see. That is connected to the hollow metallic surface. So these positive charges are collected and accumulated on the surface of that spherical surface. So as the time increases, the number of charges on the metallic surface increases gradually. So you can maintain a high potential difference with respect to ground. Ground potential we are taking as 0. Okay. So it is having principle discharging action of sharp point. That is why we are using that brush. Brush bristles always giving the charge and accepting the charge from the belt. Then charge given to a shell is uniformly distributed on surface. That is the top part we discussed. And it is using for accelerating. Accelerating means increasing energy. As for proton, deuteron, alpha particle for the what is called experimental purposes that we will discuss in later, which are the experimental purposes it is using and all those things. So I hope you clear. This is the Van de Graaff generator. Okay. So there are some points you have to remember. When the capacitor remains connected to the battery, if it is fully charged, the potential is constant. When the capacitor is disconnected from the battery and not connected anywhere, it can hold that charge for a long time. Okay, so it is also constant. Then how the electric field and potential difference, that is discussing. Potential inside the shell is constant. Okay, 1 by 4 pi epsilon 0, remember epsilon 0 q by r. Then potential outside the shell also we discussed, 1 by 4 pi epsilon 0 q by r. Remember in the first equation I told capital R. As we discussed in Gauss theorem, capital R is the radius of the shell. So that's why that came constant. Here small letter r, the second equation. Small letter r is the varying distance. So with respect to distance, that potential will vary. The electric field inside the shell is 0, that we already learned. The electric field outside the shell is 1 by 4 pi epsilon 0. Remember epsilon 0 q by r square. So this is the basic difference between potential and electric field due to a shell. So when two charged bodies are made contact each other, the charge always will flow from higher potential to lower potential, that we already discussed. Okay, till they will have the same potential or potential difference become 0. So these are the important points you have to remember. And this is the variation of potential with respect to distance and electric field with respect to distance. The second picture I already mentioned in the Gauss theorem last application. From 0 to r, electric field was 0 because inside the shell. Just compare here, left side picture, 0 to r, potential is constant. So wherever electric field is 0, their potential become constant. You should study that one, because electric field is equal to minus dV by dx, we studied. So if E is 0, dV by dx is 0. That means something change is 0 means there is no change. So potential is constant. Then from the surface to outside, potential vary inversely proportional to r. Electric field varies square of inversely proportional to r. Understood? So this is the basic difference between the variation of potential and electric field due to a spherical shell. Okay, so this is our electrostatic session. So the theory almost finished. So we will look in detail about the numerical sessions. Okay, so thank you very much.